Okay, so irrational numbers are numbers that we can't write what technically is a finite decimal or as a fraction, all right? So one type of irrational number is what we call a surd, okay? And a surd is any number that is under a radical sign or the square root symbol that then can't be simplified to a whole number. So I guess if we think about the square root sign, um, any number, any perfect square that is under the square root sign can be simplified. So if we have a look at these numbers there, square root of 9, 16, cube roots or fourth roots, but we'll keep it to square roots at the moment. They can all be simplified, okay? So in short, any number that is under a square root sign that is not a perfect square is an irrational number or a surd. So I think it's really quite beneficial for us to have a list of all the perfect squares really handy. Maybe the first 10 or 12, okay? Because they're numbers that we need to get used to identifying, all right? So the properties of the square root sign, okay, and our square root sign, it's just a type of indice, okay, so it's actually one of our index laws. So the square root of a is in fact the same as a to the half, okay, or yeah. So, and the square root of AB is the same as the square root of A times the square root of B, which is just A to the half times B to the half. So remember, if the powers are the same, we can multiply the bases together, all right? So for us, if we have multiple numbers under the square root sign, we can split them in the same way we can divide them. So that's really important when we get around to trying to simplify a surd. So something like the square root of 8 could be written as the square root of 4 times the square root of 2. Okay, so square root of 4 times root 2. The square root of 4 is a number that we can evaluate, and the square root of 4 is 2. So the square root of 8 can be simplified as 2 root 2. I guess if we think about something like the square root of 20, actually, no, we'll leave it there. So let's have a look at example 1. The square root of 72 can be written as the square root of 36 times the square root of 2. Square root of 36, one of those perfect squares that I mentioned, is 6, and I've got a root 2 which can't be simplified any further. Now, no doubt I could have written the square root of 72 as, what else can I write? 6 twelves? 6 twelves is 72. Whoops. So I could write it as the square root of 6 times the square root of 12. Yeah, but the reason I don't opt for that option is because the square root of 6 nor the square root of 12 is one of these perfect squares. Now, we would eventually find a way to simplify it down to 6 root 2, but it would take multiple steps. So the key to simplifying a surd is to try and find the largest perfect square that we can use as a factor. Okay, so in this case, 72, square root of 36 times the square root of 2. I could have used the square root of 4 times the square root of 18, and the square root of 4 is 2, so that gives me 2 root 18. And then I would look at root 18 and think if there's something else I could use to simplify that. And there is. I can do the square root of 9. And the square root of 9 is 2, so I could write it as 2 times 3 times root 2, which is also 6 root 2. So we will get to the same answer, but if you can find the biggest perfect square first, well then life is a lot simpler for us. All right. We have a division here that we can work through. We can just split that up. So that's the same as the square root of 100 over the square root of 169. Square root of 100, it's one of our perfect squares there, which is 10. Now my list didn't quite make it up, so the square root of 169, but that's the next number in the line. Square root of 169 is 13. So that whole thing simplifies to 10 on 13. Keep working through. So let's just, if we have multiple surds and we want to add and subtract them, we just simplify the expressions as best we can. So keeping in mind our perfect squares, So square root of 50, square root of 25 times root 2. Root 2 is just root 2. Square root of 18, square root of 9 times the square root of 2. Square root of 8, square root of 4 times the square root of 2. Now again, it works much nicer for us if we put the perfect square first in our expression. Okay, square root of 25 is just 5, so I get 5 root 2 plus root 2. Square root of 9 is 3, and 2 times 3 is 6. So I get minus 6 root 2, and the square root of 4 is 2 root 2. So since all the surd expressions are the same, I can add and subtract them. So they're all root 2, so if I add and subtract those, I end up with a 2 root 2. Okay, so it simplifies down to something quite tidy. Let's go through that again. Square root of 8, root 4 times root 2, square root of 18, root 9 times root 2, and 72 is another one that we've seen before, root 36 times root 2. So again, the key is to make sure one of the numbers we put under the square root sign is a perfect square. So if we gather those together, root 4 is equal to 2, so we get a 2 root 2. Root 9 is 3, so I get a minus 3 root 2. And root 36 is 6, 5 6s are 30, minus 30 root 2. So if we add those together, 2 minus 3 is negative 1, minus 30 is negative 31 root 2. Finally, if we have a look in here, root 3, root 3, root 5, we can't simplify those surds already. And we know definitely we can't simplify them because they're in fact prime numbers. And so we just add the like surds together. So I've got a root 3 there and a root 3 there. So 6 root 3 plus 2 root 3 gives me an 8 root 3. And I've got a 5 root 5 left over. All right. So this first part of the process is just trying to simplify our surds. And to simplify a surd, we try to make the expression under the radical sign or under the square root sign smaller. Okay, give that a go.